The second part of the introduction to digital systems is going to be Boolean algebra and equations. Boolean algebra is going to be one of the most important things to understand in order to get further into this course. So it helps us get from an equation like this into something like this. Obviously, plotting all of that out is very difficult, but just going into a B naught and C is very simple. So we're going to go ahead and explain that a little bit later on. And so here's some things that you need to know. So if you have a plus sign, that means or. But if you have a multiplications, that means and. So whenever we're reading this out, if we have A plus B, that actually means A or B. But if we have A times B, or written as AB, those both will mean A and B. Yeah, okay, so here are the important principles that are required in order to continue further. So you can see that we have the and section right here, and then we have the or section right here. They have similar identities, but they're all a little bit different. So let's look at and then we'll go to or. So if you do 1 and x, that'll just be x. But if you have 0 and x, that'll be 0. Those two are very important and are a little bit straightforward. Continuing on, we have x and x, which will just simplify to x. There obviously is no x squared here, but it'd just be x. The inverse of x and x naught would be 0, because you can't have it and then the inverse of itself, so that obviously won't make sense. So if you have x times y, it's the same thing as y times x. If you have x times y in parentheses times z, it's the same thing as z times y outside parentheses times x. It follows the same way as your regular multiplication rules in this scenario. So for the distributive, if you have x plus the parentheses of y times z, you'll have x plus y times x plus z. And then finally for absorption, if you have an x on the outside multiplied by an x plus y on the inside of parentheses, that'll just turn out to be x. This will be explained a little bit later on, but we'll just go through here. So now looking at the ORs, if we have 0 plus x, they'll just give x. If you have a 1 plus x, they'll just give a 1. If you have an x plus x, same thing as and, you'll get an x. If you have an x plus and not x, you'll have a 1. If you have an x plus y, it's the same thing as y plus x. Whoops, put that right there, forgot about that. If you have an x plus y inside the parentheses plus a z on the outside, it's the same thing as z plus y in the parentheses plus x on the outside. And then going to the distributive, if you have x times y plus z inside the parentheses, it's the same thing as x plus y plus x, x times y plus x times z. And then for absorption, if you have x plus the parentheses of x times y, it's the same thing as just x. Like I said, I'll go ahead and explain those in a second. Alright, so looking at the absorption that I said earlier, so we're just going to go ahead and multiply this through. So it's going to be the and version of it. You're going to have an x times x plus an x times y. Then if you put these two together, have an x plus an xy. So obviously, we saw earlier that this is going to be equal to x, and this is also going to be equal to x. If we look at this, we know that we have an x here and an x here, but this x also has a y attached to it. So that means that no matter if the x is true, but if the y is not true, it doesn't matter. But with this x, if the x is true, then it doesn't matter what the y is. So this x will actually encompass both of those. So this would just go ahead and be x. This will be explained a little bit more in the future one whenever we go over truth tables a little bit further. So we're going to go ahead and do the same thing for the OR version. We'll have an x plus an xy, which obviously both of these are the exact same. So this would also be equal to x. All right, so working on this example here, we're going to have an x plus b inside the parentheses times an x plus c in another parentheses. So the first thing we're going to do is just FOIL this through. We're going to have an x and a times a plus an a times c plus a times b, then an a times c. So just oh, oops, this is supposed to be a b times c. Alright, so we can see that this a will just, a times a is just a, and if we move everything else down, we'll have ac plus ab plus bc. Okay, so obviously I got rid of the multiplication signs and just put them two together. Obviously they are the same thing. So like I said earlier, this a and then this would be the same. So the a would encompass the ac, so we'll have an a here plus the ab plus the bc, and then the same thing that just happened there, this will be encompassed by that, so we'll have the a plus the bc. So obviously this is a lot simpler than drawing all that. So let's go ahead and draw out a quick circuit diagram for this. So we have our a here, our b here, and the c here. So let's go ahead and draw the AND gate right here, which would connect the C to the bottom and then the B to the top. And then both of these would be going into an OR gate through here, and then we'll have the A going through here. And finally, this would be our F, or our output. But let's say we went ahead and did the first one just to see how much bigger the circuit would get and how much we saved by using Boolean algebra. So let's go ahead and grab this. Go ahead and move it over to the side. We have our A, our B. We'll also have another A and another C. You don't have to have the two A's, but it makes it a little bit easier. We'll go ahead and make two OR gates right here and right here. We're gonna go ahead and feed the C into here, and then the A is also gonna feed into here. The B will feed through here. The A will feed through here. And finally, we'll go ahead and add those two together, which will give our F. So with this, we see that we saved this OR gate right here. In this one, we only have two gates, while over here we have three gates. So in the long run, whenever we have bigger and bigger equations, we'll save more and more gates. For this one, it does look a little bit worse, but it's actually a lot easier. So we see that we have this right here with the A plus the A naught. We know from before that A plus A naught is actually just equal to 1. So we got a 1 here, and then we'll go ahead and leave this part as it is. So we'll multiply the 1 times A, B, plus A, B, oops, B, C naught. Okay, so we know that a 1 times AB or 1 times AB C naught is just what it is. So we'll have AB plus AB C naught. Okay, and then we're going to go ahead and use that rule. And we know that AB has ABC naught inside of it already. So we're just going to go ahead and remove this term, and we'll have our final answer as AB. So this is actually going to be a really easy circuit. We just have a B here into an AND gate, and that is our output. If we go ahead and do the same thing, right, if we go ahead and make the gate structure for the one before that, we'll have our A here into our A, B, C here. Okay, so this A will go here into an OR gate with an inverter here. So this one will get our first term of A plus A naught, goes through here. And then for our second term, we'll need an AND gate, which will just be A and B. And then our other term will require another AND gate, which will connect the AB from here, plus an inverter for the C. We'll go here. And then finally, actually, we have two more. So we'll need this OR gate, which will OR these two together. And then we're going to need a AND gate to finish this up. We see that instead of all these gates here, we just left with a single AND gate. Right, so this is going to be our second to last problem here. So for this one, it's going to be pretty similar. So let's go ahead and do that. We're going to FOIL again like we did earlier. So we'll get our A here and our plus A, B naught, C. Then we're going to go ahead and get our A, B, C naught. And we're going to multiply these two together, which will get B naught, B, and C naught. Alright, so this looks a little bit worse, but it's not too bad, of course. So let's go ahead and look through this. So obviously the A times A will be simplified to A. And right now that looks like, yeah, so if we have our B naught times B, that is actually 0. And then our C naught times C is also 0. So this term will actually just go away. And then we'll have an A, B naught C plus an A, B C naught. So we see, like the steps before, that the A has this term and this term in it. So the A, B naught C plus the A, B, C naught would actually just be A. So instead of having all those gates, we actually have 0 gates for this one, and we just plug A into our output. Okay, so this is the same equation that we had from before for our, in the intro. So we know what this is going to simplify to, so let's go ahead and prove that it simplifies to that. So the first thing is we're going to go ahead and look into the inner parentheses right here. We're going to go ahead and follow that through. You have a, b, make sure you have your outer parentheses, plus your c, plus your a, b naught, b, d, plus a, b naught, times c. Okay, so if we go ahead and look at this term, we'll have a b times a b naught, which will give a 0. So I'll pull the 0 down here, plus our a naught, b naught, and then we're going to multiply all of that by c. So let's go ahead and do that. So we'll have our a, b naught c, and then 0 times c is 0, plus a naught, b naught, c. Alright, so let's go ahead and look at these two terms. We see that with these two terms we have a similarity. We have b naught c here and b naught c here. So let's go ahead and factor that out. We'll have b naught c times a plus a naught. And a plus a naught is equal to 1. So in actuality, we have b naught c times 1, which is equal to b naught c. So just like that, we proved that parentheses a b naught times c plus bd close parentheses plus a naught b naught times c is actually just equal to b naught c.